a second example of being able to use the fundamental theorem of calculus, this time with trigonometry. So we want to evaluate the interval negative pi fourths to 7 pi fourths using the fundamental theorem of calculus. And we want to, again, discuss whether or not the result is consistent with a specific diagram. So we're going to start by defining the function f as sine x plus cos x. And if we take the antiderivative of that, now remember the antiderivative of negative sine is negative cos x, okay? The derivative of cos is positive sine x. And so the integral from negative pi fourths to 7 pi fourths is going to be equal of our sine x plus cos x dx is going to be equal to minus cosine of x plus sine of x. And that's going to range from minus pi fourths to 7 pi fourths. All right, so now we just have to use the fundamental theorem of calculus, which says that we're going to take f at b and subtract f at a. And so what's that going to work out to be? Well, f at b means that we're going to substitute 7 pi fourths in. Okay, so that's going to be negative cos 7 pi fourths plus sine 7 pi fourths. F at a, we're just going to substitute negative pi fourths in. So that's the negative of cosine of negative pi fourths plus sine of minus pi fourths. All right. For most students, this is where it starts to become a bit of an issue because we want to get exact values. We don't want to just throw this in our calculator. And what you might have to do is you might have to remember on the unit circle what's going on at 7 pi fourths. Okay, so 7 pi fourths and also negative pi fourths. Okay, so if you were to go this way, okay, all right, this theta, and I'm going to call that theta 1, is actually negative pi fourths. Okay, so remember, usually when you go clockwise, that's a negative. And then this way, I'm going to call that theta 2 is 7 pi fourths. And you might remember that at this point, the x is going to be positive root 2 over 2, and the y is going to be negative root 2 over 2. All right, so going back to your trigonometry, and you should remember that negative pi fourths and 7 pi fourths are the same value. Now, remember, your x value is the cos of theta, and your y value is the sine of theta on the unit circle. And so what we could do is we could just substitute these root 2 over 2 and negative root 2 over 2 back in for your cos and your sine functions. Okay, so let's hold on to this because this is the important stuff that we get out of that. Right, and all this can just go away because we just used it to be able to get to that angle. So let's just move that down here. We're going to keep that on tap because we need it. And so this is going to be the opposite of, this is our x value, right, which is root 2 over 2, plus the sine of 7 pi fourths, which is the y value, which is negative root 2 over 2, minus, so the opposite of cos of pi fourths, negative pi fourths, which is the same thing, because remember, these values, 7 pi fourths is equal to negative pi fourths. They're coterminal angles. And so this is a negative root 2 over 2. And then we just say this is going to be plus another negative root 2 over 2. And if we simplify this, this just becomes the opposite of 2 roots of 2 over 2 minus the opposite of 2 roots of 2 over 2. These 2's cancel out. And so we end up with negative root 2 plus root 2, which is 0. All right, now, Does that answer make any sense? Well, let's check it in our calculator first of all. Right? So I'm going to change the mode back to the symbolic manipulator. Called math print. Okay. I'm going to put out of here. Remember, to be able to access this, you hit the math button. From now on, what I'm going to do is I'm just going to hit math 9. Okay. In your calculator, it might be different, but math 9 brings up fn int. Right? And we have pi, negative pi over 4, excuse me. So we're going to say negative pi over 4. And up here, we have 7 pi over 4. And remember, we had sine x plus cos x. And then we had our dx. And we hit enter. And look what it gives us. It gives us this crazy number, negative 1.1592 e to the minus 13. Well, that's just scientific notation saying negative 1.16 approximately times 10 to the minus 13. Okay, so if I was to go through and just write this out from our calculator, calculator says negative 1.16 times 10 to the minus 13th power. All right, and isn't that really just going to be opposite and 12 zeros? And then 116, which is approximately 0 anyway. The calculator will not give you an exact answer, okay? Only calculus will. Sometimes this might give you a 0, all right? But a lot of times it's going to do this scientific notation to approximate it. The graph, though, let's go back to the graph. Well, this graph suggests that these areas are the same area. They're symmetric. They just cancel each other out. Okay, so notice that at 3 pi fourths, the function is symmetric at that point. Okay, so it just makes sense that they are going to cancel one another out. Okay, so it should be consistent because technically what's going on is that this is the square root of 2 and this is the square root of 2. Okay, so those two areas are root 2 and root 2, but because one of them is below the axis, that means that one of them counts as a negative, the other one counts as positive, hence we end up with the 0. All right, so it does make sense that that should be our answer. All right, so one more example before we quit this video. Right, now this one just says we want to use the fundamental theorem of calculus. We don't have to, and then we can sketch it just to make sure, but we could just use our calculator to check. Before we set this up, let's rewrite this integral as integral of 1/3 to 3 6 dx minus integral of 1/3 to 3 6x to the minus 2 dx. All right, so this is a very common technique. We're going to start using those rules that we looked at in the previous section, and we're going to split apart two terms, two integrals. We're carrying the sign over. And just like we did with differentiation, anytime we have a denominator with a variable in it, and it's just a monomial, we're going to swing that up to the numerator. Now we can go through and we can evaluate each of these by taking the antiderivative. Okay, so right here, we're going to take the antiderivative, and right here, we're going to take the antiderivative. Antiderivative of 6 is 6x. And then antiderivative of 6x to the minus 2 is going to be 6x to the minus 1 divided by minus 1. And the limits of integration are going to be from 1/3 to 3. Another way that we could write this is going to be 6x plus 6 over x, if we were to algebraically simplify that. Right? So hopefully that makes sense. You have a negative divided by negative to positive, and then we just take this, move it back down to the denominator. We're going to substitute 3, we're going to substitute a third, and we're going to evaluate it. So this becomes 6 times 3 plus 6 over 3. minus 6 times 1/3 plus 6 divided by 1/3. So we know 6 times 3, 18. 6 divided by 3, 2. We know 6 times 1/3 is 2. And then 6 divided by 1/3 is really the same as 6 times 3 over 1, which is 18. All right, we're going to carry the negative sign as well. And wouldn't you know it, that happens to give us 0 as well. All right. Now, we could go through and we could graph the function. In fact, let's do that. So if we have y equals 6 minus 6 over x squared, and we got a whole bunch of other stuff there. So divided by x squared. And I'm just going to bump this over. There it goes. And we just graph it. And I'm going to have to zoom standard. All right. What's happening with this is that there's symmetry involved with this. All right. It's not necessarily continuous at 0 either. Okay, so that's an issue. But at 1/3, there's some area below the axis and some area above the axis. And of course, what we can always do is we can just use the fn int function. So I'm going to do math. I'm going to hit 9. Remember, we had 1/3, and then we had 6, or I'm sorry, we had 3, and then we had 6 minus, I think it was 6 over x squared. Let me verify that. X squared dx. Right. And then we can just go ahead and graph that. Oh, sorry. Quit out of this. We can just hit enter. All right. And doesn't it give us that weird scientific notation again? And it's really just going to be 0. Okay. So that's how we can use our calculator to check. We can use the graph to verify it. But the best way to be able to find the exact area is just to use our good old calculus. Okay. So what I'm going to do in the next few videos is I'm just going to do a few more of these fundamental theorem of calculus problems, and then we'll be done with this section.